Okay, we're going to look at capacitors in series and parallel. Series circuits are where we have different circuit elements sequentially, one after the other. So basically, whatever current passes through the first must pass through the second. Parallel means that they're both connected to the same potential difference, and thus you're going to have the same voltage. But the current is going to break off and go through one element, or part of it will go through one element, part of it will go through another element. So we'll take a look at these two different cases as they apply to capacitors. We don't spend as much time with the capacitors as we do with the resistors, but this is some of the circuit analysis that's very important to trying to figure out how a particular electronic circuit or device is going to behave. So again, a circuit is a collection of objects usually containing a source of electrical energy, such as a battery or some other electrical source. We call it an EMF. It's connected to elements that convert electrical energy into other forms. It's important to understand that the term circuit means that it goes around in a circle. It returns, it leaves this energy source, and it returns to the energy source. Circuit diagram is usually what we use to represent particular circuits. And these are useful because they simplify the different circuit elements. We don't have to sketch precisely what each one looks like. Everything is represented by a particular symbol. Here we have a parallel circuit. This is a source of energy, or electrical energy, comes from this battery right here. Chemical energy is converted to electrical energy. And this is called parallel because the wire connects to the first capacitor and also connects to the second capacitor. Reverse that. This is C1, this is C2. So basically, if we were to send current through this, and that's not a great example for this because the capacitors, in fact, when they're fully at equilibrium, are open circuits. But if we connect these capacitors, some of the current will flow to the positive plate here, some of the current will flow to the positive plate up here. So they're both in parallel, they're both connected to the positive terminal, and they're both connected to the negative terminal. So when we look at this, we want to analyze the total capacitance of this particular circuit. We put two capacitors in parallel. What is the result going to be? Well, if they both have the same voltage across them, we're just basically going to have the same voltage, different currents if they're different capacitors as they're charging. But basically, the capacitors will charge until they're completely full. But the capacitance on the first one and the capacitance of the second one is going to determine how much charge they build up. And that's completely independent of what the other one is doing. Both will charge according to whatever voltage is coming out of the battery because they're in parallel. So here, the total charge, when we consider the total charge for capacitor 1 plus capacitor 2, simply depends on the voltage of the battery and also the individual capacitance. So we can say here that the two capacitors act like one bigger capacitor. Now, going back here, this capacitor gets Q1, this capacitor gets Q2 of charge. Now, an equivalent capacitor, which is bigger, would be able to store the same amount as C1 plus C2. So this is very simple. For capacitors in parallel, we simply add the capacitance together. And that tells us, basically how much charge this total circuit can store for a given voltage. And again, here is our sort of schematic diagram of what's going on. Well, I should say representative diagram of what's going on. This is what a battery looks like. This is what parallel plates capacitors would look like if they're just two parallel plates. And notice we've replaced that with a circuit diagram where the battery is represented by this symbol of parallel lines of unequal length, and the capacitors are represented by these symbols, these parallel lines, which have equal length. So here are some of the circuit diagram symbols that we use, again, for a battery or EMF, and therefore capacitors. Sometimes you'll see more than just 2 lines for an EMF source. Sometimes they'll use 4 lines or more, but really, for our purposes, they're meaning the same thing: a source of voltage. Now here is an example of 4 capacitors in parallel. Okay, they're all connected to this positive terminal. It just branches off into these 4 different wires. So everything on this side of the capacitors has the same positive voltage as the battery. Everything on the opposite side has the same negative voltage as this one. So the potential difference across every capacitor is going to be 18 volts. So what we can first do is take these 4 and say, well, this is just going to act like one big capacitor. What is the equivalence going to be for that case? Well, C1 is 3, C2 is 6, C3 is 12, C4 is 24. Add all those up together, and we get an equivalent capacitance of 45 microfarads. Okay, so given that total capacitance of this particular circuit, we can then calculate the total charge stored. And remember, micro means 10 to the minus 6. So we have capacitance, 45 microfarads is 4.5 times 10 to the minus 5 farads. We have the voltage from the battery, and the total charge stored on this, on the positive side or on the negative side, is 8.10 times 10 to the negative 4 coulombs. So parallel is really easy. You want to find the equivalent capacitance? Just add up each individual capacitor together. I should say, take the sum of each individual capacitor. Now, when we do something in series, we've got to be a little more careful. They're still connected to the battery. However, think about what's happening. The battery provides 18 volts. Well, let's say that it provides 18 volts. With these capacitors, you will get a voltage difference across this one and a voltage difference across this one. When we have circuits in series, the total voltage drop is the sum of each individual element in that series, which means that if this is 18, I'll lose some of the 18 here and some of the 18 here. Okay? No longer are C1 and C2 under the entire voltage of this battery. It's now divided up. Here's the other thing that we know. The current that flows from the battery to this first capacitor, okay, however much charge builds up there, Q, is going to be equal and opposite to this side, which is negative Q. Now, if this side is negative Q, to conserve charge, this side of this capacitor must be positive Q, and again, this side must be negative Q. All right, think about this. These are actually open circuits. We can keep building up charge up to this point, but eventually it's going to stop. All right? We can have charge move back to the battery on the negative side. But again, what happens to this capacitor is going to be the same in terms of this capacitor. It's related to how much current flows in our series circuit. So with this in mind, when we're dealing with capacitors in series, the amount of charge on one capacitor is going to be equal to the amount of charge on the other capacitor. Now, going back to our equation, when we're looking at the equivalent capacitance for these series, we have to make sure that both capacitors have the same amount of charge, okay? And therefore, if each capacitor in series has the same amount of charge, we know that C is equal to Q divided by V. Therefore, V is equal to Q divided by C. Thus, the voltage across each capacitor is going to be equal to the charge, which is going to be the same for both, divided by the capacitance of each. So, for instance, going back to our series capacitors, let's go back right here. Let's say C1 is twice as big as C2. Well, what that means is that even though they have the same charge across them, a larger capacitance, okay, indicates that to get the same charge on the capacitor that's half as big, we need twice the voltage drop. So a bigger capacitor will have less of a voltage drop to get the same amount of charge. All right, so let's go back to our derivation right here. With that in mind, if Q is all the same here, okay, an equivalent capacitor, or 1 over an equivalent capacitor, again, V, the total V, V1 plus V2 plus V3, would be equal to the total voltage drop of an equivalent capacitor. We use this right here, make the substitution here where all the Q's are the same, the Q's will cancel out on both sides of the equation, and we get 1 over the equivalent capacitance is equal to the sum of the reciprocals of each individual capacitor. Okay, a little bit complicated, but notice that this is a little bit different from what we had with parallel. With parallel, C equivalent was just equal to the sum of C1 plus C2 plus C3 plus however many capacitors we had. Here, it is 1 over the equivalent capacitance is equal to the reciprocal of C1 plus the reciprocal of C2, so on and so forth. So in doing this type of problem, math is a little more difficult, but it's really not too much of a challenge. Let's take our 4 capacitors that we had before, and let's find the equivalent capacitance. 3, 6, 12, and 24. So, these are going to act like one single capacitor. What's going to be interesting is the equivalent capacitance is actually less than each of the individual capacitors, which means that since 3 is my smallest capacitor, my equivalent capacitance is actually going to have to be less than 3. Okay, so we have 1/3, well, 1 over 3 microfarads, but let's consider it as a fraction, 1/3. 1/3 plus 1/6 plus 1/12 plus 1/24. Our least common denominator right here is 24 microfarads. So this is 1 plus 2 over 24 plus 4 over 24 plus 8 over 24. Okay? Add those all up together and we get 5 over 24 microfarads. That's equivalent capacitance. We take the reciprocal of this because we want the equivalent capacitance. We don't want 1 over the equivalent capacitance. That's 24 over 15 or 1.6 microfarads. So these 4 capacitors in series actually store less charge than each individual one would if it were connected to this battery. So in this case, 1.6 microfarads is less than 3, 6, 12, and 24. Hooking up to our 18-volt battery, how much charge do we store? Well, 1.6 times 10 to the negative 6 times 18 gives me 2.9 times 10 to the minus 5 coulombs. So much less charge is stored for that case when the resistors are placed in series than they were for parallel. Now, in analyzing circuits, a lot of times we want to take more complex circuits and simplify them to an equivalent. Okay? When we had the parallel capacitors, we took parallel capacitors and reduced them to an equivalent capacitor, which was equal to, I should say, capacitance was equal to the sum of the individual capacitance. For the series, it was the reciprocal was equal to the sum of the reciprocals. When we have more complex circuits with both parallel and series, we want to take the parallel circuits, reduce them to a single equivalent, do the same with the series, and keep simplifying it more and more. Let's take a look at a case where we're going to take parallel and series and keep repeating the process of reducing it to an ever more simple setup, and then find what's going on. Okay, this looks really complicated. What we have here are 6 different capacitors, where some are in parallel and some of the parallels are in series with the parallel. Okay, how do I handle this? Identify our circuit elements that are either purely in parallel or purely in series. Reduce them to an equivalent. So, let's start with our two parallel. These two parallel are in series with a 4 and in series with an 8. So we can't do anything with the series yet, but we can simplify the parallel. These two become this, these two become this. We're left with, instead of 6 capacitors, we're left with 4 capacitors. Now I have series and series. These two sets of series are in parallel with one another. So these two series become 1, these two series become 1, and then finally the two parallel, this one and this one, can reduce to this one. Okay, let's go through each step. For the first case, I'm going to take the equivalent of this one and the equivalent of this one. They're in parallel, so I can just add the capacitances, and that's really simple. 1 plus 3 is 4, so the 1 plus 3 becomes 4. 6 plus 2 becomes 8. There's your 8 right there. And now I'm to this middle state right here. Okay? I actually have 6 capacitors here, but they're now represented by 4. Let's reduce it some more. Now I take this one and reduce them to a single one. Remember, we're taking the reciprocal of the sum of the reciprocals. So 1/4 plus 1/4 is equal to 1/2. The reciprocal of 1/2 is 2. Same thing here. 1/8 plus 1/8 is 1/4. The reciprocal of 1/4 is 4. So the two 4 millifarads, I had to take a look at that, two 4 millifarad capacitors become a 2 millifarad equivalent. The two 8 millifarad capacitors become a 4 millifarad equivalent. And now we have 2 in parallel. 4 plus 2 equals 6. So you can see, even a fairly complex circuit like this can be reduced to a single element, and once you have it reduced to a single element, it's very easy to predict how it's going to behave. So again, capacitance. Capacitance is the amount of charge stored for a given voltage. If capacitors are in parallel, we can simply take the sum of the individual capacitors and get the equivalent capacitance. If they're in series, we have to take the reciprocal, okay? The reciprocal of the equivalent is equal to the sum of the reciprocal.